Space amazes with its grandeur and mysteries that remain beyond our understanding. Here, giant stars live and die, supermassive black holes hide, quasars shine, beacons of ancient epochs, and molecular clouds hold the secrets of new worlds being born. What connects these colossal phenomena? What secrets do the most distant corners of the universe keep? Ahead lies an incredible journey through the most vast and intriguing parts of space. Don't miss it. Subscribe and like to learn more about the mysteries of the universe. Deep within the universe exist objects that truly captivate the imagination. Gigantic stars whose sizes and luminosities defy conventional notions of scale. Among them, hypergiants hold a special place, rare and short-lived luminaries that occupy the extreme upper positions on the Hertzsprung-Russell diagram, shining with luminosity classes exceeding -8 meters. These stars possess masses reaching up to 250 times that of the Sun and emit millions of times its brightness. Their surface temperatures range from a comparatively cool 3,200 Kelvin to scorching 35,000 Kelvin, and their lives are so turbulent they last only a few million years, as the most powerful nuclear reactions rapidly consume their colossal fuel reserves. Among the most striking representatives of this class are Stephenson 218 and VY Canis Majoris. The first, located in the Stephenson 2 star cluster, has a temperature of only about 3,200 Kelvin and can radiate up to 630,000 times the Sun's luminosity, occupying the extreme edges of the region of cool but incredibly bright stars. The second, situated just 3,900 light-years from us, is a red hypergiant with an estimated radius up to 1,420 solar radii, larger than the distance from the Sun to Jupiter. Its volume is 3 billion times that of the Sun, and its mass reaches 17 solar masses. Despite its relatively low surface temperature of around 3,500 Kelvin, it emits between 400,000 and 500,000 solar luminosities, ranking among the brightest and most massive red supergiants in the Milky Way. Such objects are true colossi of space, born to shine unimaginably bright and die in a grand cataclysm. Why does nearly every galaxy hide at its center a monster billions of times heavier than the Sun? What causes some black holes to leave the galaxy's center and wander through its outskirts? At the very heart of most galaxies, including our Milky Way, lie supermassive black holes. Their masses range from 100,000 to hundreds of billions of suns, and they represent a key component in the structure and evolution of galaxies. These objects do not merely dominate with their gravity, they shape the behavior of stellar systems, regulate star formation processes, and can determine the appearance of entire galaxies. As observational technologies advance, more of these objects are being discovered, some of which challenge our previous understanding of the possible scale. To date, the most massive confirmed supermassive black hole is Phoenix A star, located 8.5 billion light-years away in the Phoenix cluster. Its mass reaches 100 billion suns. In the galaxy Holmberg 15A, situated in the constellation Cetus and 700 million light-years away, the black hole weighs about 40 billion solar masses. There are also more modest, yet still grand examples. The black hole in galaxy NGC 4889 in the constellation Coma Berenices has 21 billion M-suns, and Q0906 plus 6930 in Ursa Major has 10 billion M-suns. Even in the tiny dwarf galaxy Henais 2-10, only 30 million light-years away, a black hole with a mass of 3 million suns has been found. Surprisingly, some of these black holes are not located at the centers of their galaxies, but on the outskirts, which may indicate a rich and turbulent history of migrations and mergers. Could quasars be seen as peculiar chronicles of the past, capable of revealing how the universe evolved? Why do quasars, tiny in appearance, emit more light than entire galaxies? Quasars are some of the brightest objects known in the universe. Despite their point-like appearance resembling stars, they conceal colossal scales of energy and distance. Modern research shows that quasars are the active nuclei of young galaxies, where a supermassive black hole consumes surrounding matter. This matter forms an accretion disk, heats up, and begins to emit enormous amounts of energy. The luminosity of a quasar can exceed the combined brightness of all the stars in galaxies like our own by tens or even hundreds of times. The cause of such powerful radiation is not only the intense accretion of matter, but also effects predicted by Einstein's general theory of relativity, in particular, gravitational redshift. One of the most well-known quasars is TON 618, discovered back in 1957 during a search for faint blue stars. At that time, its nature was unclear. In photographs taken at the Tonantzintla Observatory in Mexico, it appeared as a definitely purple star. Only in the 1970s, after the detection of its radio emission and emission lines, was it understood to be a quasar with a redshift of Z greater than 2.2, meaning an extremely distant object. It is associated with one of the most massive known black holes, with a mass reaching 66 billion times that of the Sun. Quasars are observed at enormous distances, and it turns out their peak activity occurred around 10 billion years ago. Today, they serve as cosmic beacons. Thanks to their light, scientists study the evolution of galaxies, the distribution of matter across vast distances, and features of the early universe. By analyzing the hydrogen absorption spectral lines stretched along the line of sight, astronomers reconstruct the structure of the cosmos at the epochs when the first galaxies were just beginning to form. Despite their great distance, quasars do not lose brightness. They remain fixed on the celestial sphere and have no parallax, making them ideal reference points even for interplanetary probe trajectories. What secrets do molecular clouds hide if their main substance, H2, is practically impossible to observe directly? Molecular clouds are the densest form of the interstellar medium where molecules can exist, primarily hydrogen, H2. These clouds play a key role in the process of star formation and are therefore often called stellar nurseries. However, molecular hydrogen itself is difficult to detect, so its presence is inferred from the emission of another molecule, carbon monoxide, CO, assuming a constant ratio between its luminosity and the mass of H2. Although this assumption is not always accurate, it remains the main method for identifying such clouds. Giant molecular clouds, GMCs, contain between 10 to the 4th and 10 to the 6th solar masses of material, span tens of parsecs in diameter, and have an average density of 10 squared minus 10 cubed particles per cubic centimeter, which is significantly higher than the interstellar medium density near the Sun, about 1 particle per cubic centimeter. Their internal structure is complex, consisting of filaments, sheets, bubbles, and clumps. The densest regions, called molecular cores, can have densities exceeding 10 to the 4th to 10 to the 6th particles per cubic centimeter. These cores are associated with carbon monoxide and ammonia, and when dust concentration is sufficient, can absorb background light, appearing as dark nebulae. The most well-known local GMCs in our galaxy, the Orion Cloud and the Taurus Cloud, are part of a structure called the Gould Belt. The most massive complex is Sagittarius B2, located at the galactic center about 120 parsecs from the core. It serves as an important site for discovering new molecules, as the Sagittarius constellation region is particularly rich in chemical elements. Besides GMCs, there are smaller-scale molecular clouds known as Bok globules. These are isolated, gravitationally bound, and their masses do not exceed a few hundred solar masses. In 1984, high-latitude diffuse molecular clouds were also discovered, with characteristic densities around 30 particles per cubic centimeter, located outside the plane of the galactic disk. Just as dark matter forms the invisible skeleton of the universe around which enormous galactic filaments organize, what lies in the void between these filaments and the Great Walls? Could these cosmic voids reveal something new about the nature of the cosmos? On the largest scales of the cosmos, matter organizes into colossal structures, galactic filaments or fibers. These gigantic formations consist of extended clusters of galaxies, ranging from 50 to 80 megaparsecs in length, approximately 163 to 260 million light-years, and lie between vast voids called voids. Together, they can form even more grandiose shapes, so-called Great Walls, flat complexes made up of numerous clusters and superclusters of galaxies. The space between these filaments and walls is filled with diffuse and extremely hot gas, with temperatures reaching tens of millions of degrees and densities of only 1 to 10 atoms per cubic meter. According to the standard model of the universe's evolution, filaments form along the network-like flows of dark matter. It is dark matter that serves as the framework for the formation of the entire large-scale structure. It gravitationally attracts baryonic matter, the ordinary substance that we can observe. This material network, forming a sort of skeleton of the universe, is known as the cosmic web. The grandeur and mystery of space continue to inspire scientists and astronomy enthusiasts around the world. From giant stars and supermassive black holes to bright quasars and molecular clouds, each of these cosmic objects tells its own unique story about the origin and evolution of the universe. By exploring large-scale structures, we gain a deeper understanding of how our galaxy and the entire surrounding cosmos are organized, from the smallest particles to the magnificent galactic filaments. Stay tuned to our channel so you don't miss new, exciting discoveries and learn even more about the secrets and wonders of the universe. Subscribe and stay updated with the latest space news.